There we go. We are indeed going to start chapter 3 here. And what we're going to see is chapter 3 is where we're finally going to get into some actual data. Data. We're actually going to get in and see numbers and things of that ilk. So data, that's what we're thinking here. So the most initial place to start, the best place to start rather, I should say, we should start talking about what we call measures of central tendency, which is exactly what it sounds like. Where does the data kind of center around? Where does it clump around? That's what we're going for. Where does it center? And so the first kind of and the most immediately obvious measure is the mean, which is a fancy way of saying it's just another word for the average. You can call it the mean or you can call it the average, just depending on your flavor. That's all there is to it. The mean is computed by adding all the values in the data set and dividing by how many values you have. You got 22 values, you add them all up and it comes out to 1,300. Then to find the mean, you do 1,300 divided by 22. So that's straightforward. So the mean is pretty cool. Sometimes it's called the arithmetic mean. It turns out there's other kinds of means or averages that you may not have dealt with before. So what else is new? Well, the way we actually calculate it. The first thing we have to note is that there's going to be two types of means that we're going to talk about. They're both arithmetic, but what I mean by that is we have two different means that we care about. We have something called the population mean, and we use this Greek symbol. It's not a U, it's not an M, it's a mu, like the 151st Pokemon. It's a mu, that's how you write it. I'll attempt to draw it here for you. Mu, that's the best I can do. Mu. What happens is if you have a bunch of data values that represent data from a population. So for instance, let's say you were somehow able to go out into the entire US population, all adults, let's say, men and women, and you were able to collect their blood pressure. Let's say that first number, the systolic, I don't know, but whichever that first number is on blood pressure, if you had all those observations, and you're looking at roughly 300 million observations, somewhere in that ballpark, which again is a lot. But if you had that, each of these X values just represents each of the different data points. Oh, the first person, their blood pressure is 125, that first number. Oh, the next person, their blood pressure is 115. The next person, 140. Those would be all the data values. To find the mean, you would need to add up all of those data values and divide by, well, you have 300 million people, so you got to divide by 300 million. Now, this is the formula for it, and this one doesn't look so bad. It's just saying add them all up. It uses ... because this is defined for however many you have. If you have 5,000 data values, capital N would be 5,000. You'd add them all up, divide by 5,000. This over here is the exact same thing, just written in what we call summation notation. This capital sigma here is telling you to add a bunch of things up. These are all the things you're adding. We just use a subscript as a notation tool. Then you divide by how many you have. But you can just think about it in the simplest terms. So we have a population mean, mu. We also separately talk about a sample mean. A sample mean. And we call that bad boy, we call it, you can literally say it as X bar. It's an X with a bar on top. Now you go down here and you look at the computation. Okay, we're using a lowercase n to represent the sample size, the number of things in the sample. So a lowercase n is the sample size. Up here, we used a capital N to represent population size. What's the difference? Why do we care so much about it? Well, we have to make the distinction between the sample and the population, because remember, the population values is usually something that we can't get. We would like to get it, but we can't. We are just so gosh darn limited in what we can do. 300 million Americans, get out of here. You're not going to go and get every blood pressure reading for 300 million people. So what we're usually interested in, though, is that population mean. So the whole point of statistics, specifically inferential statistics, we would actually go get a sample. You can't get 300 million Americans? Okay, let's go get 500 Americans. That might be a lot more doable. It is. We'll take those 500 Americans. We'll compute the mean of that sample, X bar. We'll compute it. We'll just add up the blood pressure readings for those 500 Americans, divide by 500. Whatever value we get out of that, we might try and infer things about the population it came from. So X bar is nothing more than a tool. It's a tool that's going to let us do inference on what we really want, which is the population mean, but we usually just can never get the population mean. All we can do is infer things about it from the sample. Other than that, the computations for both are exactly the same. They are literally exactly the same. Just they're using a lowercase n down here because that's what we use for the sample size instead of the population size. This is actually going to be something that can cause a lot of confusion. So we're going to be very careful and explicit with how we deal with it. Okay, but nevertheless, the following data represent the travel times in minutes to work for all 7 employees of a startup web development company. So we actually are talking about a population here. We're talking about a population, and it's because it's a pretty small company, and it's what all we care about is that company, the 7 employees in it. The first person, it takes them 23 minutes to get to work. The next person, it takes them 36 minutes to get to work, and so on and so forth. So this is the entire population. So for this very narrow example, we are able to get population data. In general, of course, we're not. But for a nice little easy example, we can pretend like it. So here's what I'm going to do. I'm going to calculate the population mean. I'm fully comfortable using a mu and saying, all right there, Pilgrim, I'm going to have to add these all up. And I'm going to use my handy dandy calculator. And then what am I going to divide by? 7, exactly. Add them all up, and you divide by the number of data points you have, which is 7. So it's really exactly like the average you already understand and know. Nothing wild going on here. So let's add up that numerator. You can follow along at home. In fact, for the rest of the semester, you're really going to want, if you're coming to class in person, you're going to want your calculator out and ready because we're going to be using it like no one's business. So you want that calculator out. And so now we're going to do the calculation. On top, you're going to get 174. You're going to get 174 on top. On bottom, you're going to get 7. So now you do that computation, 174 divided by 7, and we'll round it to about 2 decimal points. Dividing by 7 can usually be a perilous business. It's about 24.86. So when do you know to round? Well, you kind of know it when you see it. If you get a number that just keeps going and going in your calculator, you're very likely going to want to round if it's a final answer. And then usually it's clear, like your online homework will say round to 3 decimal points. It's usually pretty straightforward, or round to the nearest thousandth. So this is the population mean Now, it's a little deceptive because I just told you how it's usually we're not going to actually get the population mean in practice. But if you have 7 people at your company and your company is the population, it's doable. If you had 750,000 people at your company, maybe it's doable if your company keeps good records and information like that. But if you're talking about their drive to work, I mean, that's numbers are always changing. You know, it's not going to be easy to get data for all 750,000 people. So instead, we're going to take a simple random sample of 3 employees. So I'll show you an easy way to take a simple random sample. I'm just going to number these, and then 5 happened to be the 5th one. That's the first person is 23, the second person's drive was 36. I'm going to go to Google, and I'm going to say the magic words. Google is a real living human being. I don't know if you guys knew that. Google, it lives in like a mansion, and you can talk to it. It understands what you're saying. It can even portend the future. It's a little bit of a seer, if you will. Of course, that's just me buying time. I'm going to go to Google, and I'm going to say, Google, pick 3 random numbers from 1 to 7. Calculating. And let's see what we got. And the Google said, I shall select the numbers 4, 2, and 6. So I just took a simple random sample. And the Google, using its randomization, selected 4, 2, and 6. So really, we just need the numbers for that. Let me circle that a little bit better. So remember, the 2, 4, and 6 themselves, those numbers are not going to be in the calculations. It's just saying take the second person, the 4th person, and the 6th person's data and calculate the sample mean for that. So in the first case, the sample mean is going to just be, well, 36 plus 18 plus 26. And now we're not dividing by 7, we're dividing by the size of the sample. We only took 3 people, so we're just going to be dividing by 3. Doll that up, do the numbers. I'll use my handy dandy calculator. Again, it's a pretty straightforward process thus far. And now the sample mean is about 26 point, I'll round to 2 decimal points, 26.67. So that's all we did. I picked 3 of them at random. I used the Google to do it. Now, let's again see the forest for the trees. This thing, mu is the population mean. That's what I really want. That's what my heart desires. But in practice, if you had 700 million things you're trying to, that's the size of your population, you're not going to get it. So instead, you're going to need to take a sample. So this is the true population number that in practice, I'm never going to actually know. This is the sample mean we're using to estimate this number. Is this a good estimate? You know, it kind of passes the eyeball test. It's close enough. It's not too far. It's like within 10%. But that's, you know, just the eyeball test is not going to be enough. Although we don't get into super hardcore analytics over, you know, whether or not we have good sampling. And so that's all we really need to do here. Let's do it once more. Let's try again. Nothing wrong with that first sample, but we're just going to do it again just for fun, for the practice of it. So now I'm going to go back in and I'm just going to have it give me another 3 numbers that occur between 1 and 7. And this time the Google told me, take the second number, the third number, and the 7th number. All right. So we're going to do 36 plus 23 plus 43. This is a completely different sample now. This is a different sample from the population. There might have been some overlap, as we saw, but I used a new sample. Once again, we're just dividing by 3. And now you can do this computation at home. You're more than welcome to. I'm happy for you to. Now let's see. 36 plus 23 plus 43. This one's going to come out a little larger. 34. Ooh. That's actually great because that illustrates a point. And it comes out to 34 exactly, no rounding necessary. Ooh, everyone say ooh. Everyone say ooh. Yeah. These group experiments never turn out the way we want. That's okay. Yeah, 34. Whoop, did someone say it at home? Wow, thank you. Thank you very much. Yes, 34. Oh, that's huge, isn't it? Now, this is a completely perfectly fine, fair sample we got. But look at it. It's way larger than the actual mean that we were trying to estimate. So would you say that this was a good estimator, this one? No, it's not. But here's the problem. Like I said, you're never going to actually know what the population mean is. You're not given that luxury. All you're going to have are these numbers here. So if this was your second sample, you saw that the sample mean was 34. Do you have any way of saying, oh, this is a good estimator? Not, well, on the surface, not really, because you don't know what the population mean is. You don't know if you've got a good estimate. So that's kind of the inherent difficulty of statistics. You can't go measure the entire population. It's impossible or it's cost prohibitive. You have to get a sample, but the sample's not always going to be perfect. So you try to get a largest sample as you can. There's things, fortunately for you, that kind of smooth that process out a little bit, but it's never going to be perfect. So I guess we can do this one. So we'll try this one out real quick. It's going to be a lot more straightforward than it looks. We're going to have to do a little wincy bit of algebra here. A professor has recorded exam grades for 10 students in her class, but one of them is no longer readable. So 10 students took an exam, she recorded them, but somehow one of their exam grades kind of disappeared, didn't it? It went away. But she happens to know the mean score on the exam was 82. She knows the mean score on the exam was 82, but the average of the 9 readable scores, excluding that 10th one, is 84. So the 82 was the mean of all 10 exam scores. The 84 is the mean just of the 9 exam scores we can see. What is the value of that single unreadable score? Ooh. Now everyone say, ooh.
Ooh.
With much enthusiasm. Thank you very much. Okay. So we're missing our 10th score. Okay. That's all right there, Pilgrim. Let's see what we can do here. Let's see the formula for the mean, can't type today, of all 10 scores. Well, it would be the first one plus the second score. Which I'm not going to write all of them out, so I'm going to say plus dot, dot, dot. And then I'm just going to say plus the 10th score. And then I would be dividing by 10. So I'd add up all 10 scores, divide by 10. But that will come out to a hard number. What's that number going to be? 82. If the mean score on for all 10 people was 82. Cool. All right. Let's put a pin in that. Let's give it a star. A little star. Because we can't do much with that anymore. Let's try this another way. All right, let's incorporate the other information. The mean of the 9 readable exam scores was 82. So here's the formula for the mean of the 9 readable scores, which is actually the name of my new science fiction novel. And let me tell you, it's very boring. Don't read my new science fiction novel unless you're looking for a sleep aid. So the mean for that, it's just going to be the first 9 scores, basically. All the way through the 9th score. And what we'll do, we'll call X10 the score we're missing that we're trying to figure out. Now we would just divide that by 9, and what should that come out to? Well, the mean of the 9 readable scores is 84. 84, exactly. Because the problem tells us the mean of the 9 readable scores is 84. So if we add up just the first 9 scores and we divide that by 9, that should come out to 84. And now here's a silly little trick. How many of you guys like silly little tricks?
I do.
Well, you do. Tricks are not just for kids because we're all adults in here. We're just gonna solve for this little business here. I'm just gonna move the 9 over, multiply both sides by 9. 84 times 9, well, let's see if we can do it in our head. 80 times 9 would be 720, plus 4 times 9, 36, so 756. And so now what we get is that X1 all the way up to X9, the first 9 scores added up, will be 756. Ooh, now here's what I can do. That's the same as these first 9 scores over here. So now I can say that I can set up this equation. I can say that adding up these first 9 scores gives me 756. Now if I just add the 10th score onto it and divide all that by 10, it'll come out to 82. Neat little trick. So now we can actually solve it. Now I would want to multiply both sides by 10. I need to just use some algebra here. And again, unfortunately, we do assume that you've come in armed with a little bit of algebra knowledge. You've either taken the math, oops, it's a plus sign. The math, what is it, 0332 or 0342 will prepare you for this course. Or you passed the TSI exam. So I multiplied the 10 over. I'm now down to this part of the formula. So 756 plus that missing 10th scores. This is not the number 10 as in we're going to actually bring it in. It's just saying it's the 10th X value. Now I subtract 756 from both sides. You'll end up with that 10th exam score being, well, 820 minus 756. 820 minus 760 would be 60. Add 4 back. So that last person got a 64 on the exam, the one that we lost a score for it. Nice part is you can always go back and review. You can review. Remember, I'm going to be uploading this video to the YouTubes later on today. In a couple hours, you'll see it on the YouTube. So this is a neat problem. It's okay. It's fun. So we talked thoroughly about the mean, the average value. Now what we need to talk about is the median. the median. It's basically this. The median is the very middle value of a data set. The very middle value of a data set. Now, it can't just be the data set in any old order you want. It has to be in order from least to greatest. Otherwise, the middle is arbitrary because I can just reorder the data set as many times as I want and constantly change the middle of it. So it's silly to do that. So I need to pick a convention. I need to pick that I need to order the data values from least to greatest and then find the middle one. Now that makes for some interesting math that we got to do, because if you have an odd data set, if you have an odd number of values, 1, 3, 5, 7, 9, 11, which was the other day, 13, 15, then you're going to have a value that is perfectly there in the middle. And it's all alone by itself in the middle there. But if you have an even number of data values, 2, 4, 6, 10, 12, 14, etc., you're going to have two values that have a perfect claim to being in the middle there with Malcolm. So we're going to have to do a special procedure for that. Okay, so from the travel time here, find the median. We already found the mean earlier, so we don't need to do that. So here's how I'm going to do it. I need to order these data values from least to greatest. So it looks like 5 is the smallest, then 18. Then there's 23, and it happens twice, and yes, I need to reproduce it twice. Repeats mean it's still important. There's two different employees who happen to have the same drive time. I don't ignore one of them just because it's a repeat. We got the 23s, then we got the 26, then we've got the 36, then we've got the 43 minute. That must be the boss of the employee, because, you know, they live 43 minutes away. They live in their mansion somewhere, and it's a good drive for them. So I suppose I'll leave a little farther out if it means I can own a mansion. Don't mention it. So we've got these 7 data values, put some nice space between them. Well, you can your eye just kind of naturally goes to that as the middle value. You can see it's right in the middle. It's got 3 on each side of it, so it's perfect. A little silly trick you can do is the cross-out method. Cross out the smallest and the largest, then the second smallest, second largest, then the third smallest, third largest, until you're left with this. If you have an odd data set, then it works out perfectly. If you have an even data set, you can't just cross out. Yeah, exactly. And then divide by 2. Exactly. If you've seen that before, and we'll do that here in just a moment. If you have an even number of data values, you're going to have 2 that stake claim for the middle. Add those 2 up, divide by 2. All you're really doing is taking an average of just those 2 values, if you think about it. But yeah, so when there's just the 7 employees, the median of that data set would be 23. We're going to learn some interesting things about the mean versus the median. The median is said to be resistant to outliers, meaning, let's say, it just so happened, let me mess with the data just a little bit. Let's say that, what if the largest value, instead of being 43, what if this was someone who really needed a job or really wanted to work for that company? They're like, look, I live a little over 2 hours away, but I'm willing to make the drive. Okay, so let's say that the largest value wasn't 43. Let's say it was 126. Let's say someone's making a little over a 2-hour drive to work. If you think about it, that would change that largest value to 126. But does that change the median? No. The median would have been computed exactly the same in that case. The median would have been computed exactly the same. So the median is said to be resistant to extreme values, either very large or if we had some very small values. The median would be resistant to that. It's less likely to change from it. It doesn't mean it's perfectly resistant, but it's a little more resistant than the mean. But think about the average, the mean. Remember that involved us adding up these numbers. So if I'm adding a 126 into the mix instead of a 43, that's going to make that number on top a lot larger. Then when I divide by 7, overall, the mean is still going to have to go up. So large or extreme values or very small values. have a much bigger impact on the mean than they do on the median. We're going to see that that's actually a topic we're about to cover, resistance. But now, let's say, oh look, my notes were going exactly where my mind was. Let's say that we have the seven employees already. They're happy. They got a nice routine going, but the company's starting to do some growing. And so now they hire an eighth employee. They hire an eighth employee, and that eighth employee really wants to work for this company. They really do. Maybe it's the boss's brother. Maybe they're planning to move, but it takes like a month or two to move sometimes, so they're just going to suck it up and do the long drive to work. Earlier, I just replaced the 43 with a large number. Here, we're adding a 130 into the mix, and the 43 is also there. But now notice the median we're going to still order the data values from smallest to largest. So 5, 18, both the 23s. The number 23 is a very bad Jim Carrey movie. 26, 36, 43, and then we're also throwing the 130 in there. Now we're finding the median. We can try our crossout method. But you have to always cross out in pairs. You can't just cross out a single number. You have to cross out its pair on the other side. That leaves us with two values in the middle with Malcolm. Two values perfectly in the middle. So like you were telling me, hey, we got two in the middle, just go in between them perfectly. In other words, take the average of the two values in the middle. Average of the two values in the middle. And it's just the two values, not all 8, so I only divide by 2. And you're going to end up with 24.5. Yeah. You're going to end up with 24.5. So we added a large value into the mix. The median went up a little bit. It went from being exactly 23, just a little bit higher, to 24.5. But now let's see what kind of impact that's going to have on the mean. And it's going to be pretty nasty, pretty mean. I apologize. I apologize for my bad puns. Now we're going to add them all up. Now there's 8 values. We'll have a little race. And this time it doesn't matter what order we add them up in, so it's okay that they've all been put in order from least to greatest. I'm going to get 304. Then remember to find the mean, I divide by 8, because there's 8 values here. And oh! Everyone say, oh!
Oh!
Oh! Get out of here. What happened? What happened? Well, the median from earlier, the median earlier was 23, then it goes up to 24.5. A little bit of an increase, but not a lot. So this extremely large value here had a little bit of an impact on the median. However, on the mean, it had a huge impact. Earlier, the mean was like 24.86, if you'll recall, of just the 7 data values. You add one an outlier most likely, onto that, and suddenly the mean goes from 24.86 to 38. And that's what it is. Can't help it. It's still correct, too. It's not incorrect just because it's not what we like to see. That's still what the average value is of these 8 numbers. But that's just how it is. That's just the way the game of baseball go. So it just depends on what you're dealing with. If you're having a data set that has some extreme values, and we're actually going to study a method in this chapter for identifying outliers, or very large or very small values. You have to decide what to do. The median may not be the best. The mean may not be the best, just depends on what you have. I'm going to skip that. It's not that interesting. And hey, look at this. Exactly what I was telling you earlier. Resistance. Resistance. A numerical summary of data, or in this case, mean, median, things that we've been studying. It's resistant if extreme values do not affect the value substantially. So exactly what I mentioned a second ago, we already saw an example of it. You got the median versus mean. So all of you out there in the Zoomosphere in class here, which statistic is resistant to extreme values? The median, exactly. That's exactly right. It's not perfectly resistant. It doesn't stay exactly the same, but it is. And remember, I like this word, statistic. Anytime you take a calculation from the sample, anytime you do some kind of numerical calculation or summary using a sample data, a sample of data, you're talking about a statistic. That's exactly what the word statistic means. Of course, we defined it back in chapter 1. When would it be better to use the median as your measure of central tendency instead of the mean? Well, when you have extreme values, which are also called outliers. You got outliers? Now that's not always true, but as like a nice little rule of thumb, yeah, you have some extreme values, you're going to want to use outliers. Right, what am I trying to say? If you have extreme values, excuse me, you're going to want to use the median instead of the mean. Pretty straightforward. That's not always true. If you don't have outliers, though, the mean is the best measure of central tendency in almost every case. Sometimes we have to use the median. We actually don't want to use the median because the mean has certain mathematical properties that make it really nice to manipulate and to use. But we don't quite go into that. Okay, so the following data represent the asking price of homes for sale in Lincoln, Nebraska. So here's a home, it's for $79,000. Another home is for $99,000. Another home in this sample is for $105,000. This is just a sample. This isn't every, do you think Lincoln, Nebraska is limited to, what is this, like 16 homes? Do you think Lincoln, Nebraska is? I don't think it is. I think Lincoln, Nebraska might be small, but it's a little bit larger than just 16 homes. So clearly we're dealing with a sample. This is a sample. It's exactly what we're dealing with, is a sample. So what we can do is we can find the mean and the median. The median is going to be nice because notice the data is already put in order for us. 79, 99, 105. It does skip over into another row, but that's okay. That just means we do our cross-out method. We do our cross-out method, and we're left with these two in the middle, the 132 and the 149. So we'll just do 132 plus 149, divide it by 2. And let's see if I can do that one in my head. Let's see, 19 minus 12, no, 19, 29, 19 minus 2, 17, half of 17 is 8.5, that it'll be 140.5. 140.5. So this is the median of this data, and we don't really, there is in statistics, there is a sample median versus a population median. We're not going to worry that much about that. Now I need to find the mean. I need to add them all up. 79 plus 99 plus 105 plus 111 plus 128 plus 130, plus 131, plus 132, plus 149. You get the idea. Of course, you can follow along on your calculators. I'm getting 2527 as the top number. So the mean here is going to be X bar I'm getting 2527. I might have put a number in wrong. It might be 2528. Is that what y'all are getting? What'd you get? No, you're fine. Let me double check that. 79 plus 99. I'll go at lightning fast speed, like everyone's internet claims it is, but it's not actually that fast. I got 2527 again, so maybe let's erase all this sequence. Yeah, like this 390, that one's pretty telling. That one's a pretty big value. So I got 2527, and there's 1, 2, 3, 4, 5, 6, 7, 8 times 2, 16 data values here. And of course, this is in thousands. You can't buy a home for $79, or we'd all just go buy a house right now, wouldn't we? Like, must probably just make 79 bucks happen if you get that deal fall in your lap. You're like, yeah, I'll just go borrow 80 bucks from someone real quick. Oh, you want me to pay you back 150 bucks? Okay, that's still a good deal on a house. So we do 2527 diviso por 16. We get 157 point. We'll round to whatever. We'll just round to 1 decimal point because I ran out of space. 157.9. That is a 9 at the end there, and not a mummy of some kind. There we go. It's a little better. So the average of the sample, that's why I used X bar. That's why I used X bar. The average of the sample is about 157.9. 157.9. So which is about $157,900. So the question is, this was a sample of 16 homes. There's probably thousands of homes in Lincoln, Nebraska. So can I go around and I say, you know, the average home value, the average price of a house in Lincoln, Nebraska right now is about $157,900. Can I say that? No, not quite, because this is just a sample. What I can say is I estimate. You kind of just put some qualifiers on it, some things, some words in there that make it say, I'm not definitively saying this is the average, but from the data I've gathered, it appears the average home value in Lincoln, Nebraska, or sales price is about $157,900. That's what you can say. You can't say it's definitively true, but that's our best guess. I'm not going to worry about making a histogram out of it. Just remember, you can be skewed left, you can be nice and symmetric, or you can be skewed right. The interesting thing about the different shapes of distributions here is that whenever you have skewed left, what that means is that there are some small values. And while there's not a lot of them, the values are so small that they drag the average value down because the mean, remember, is not very resistant to outliers. They don't drag the median down as much. So suddenly you drag the mean below the median. But if you had perfectly symmetric data on your histogram, if you had roughly the same amount of data on both sides and they behave a certain way, the mean and median are going to be exactly the same. But if you have data which is skewed right, that means there's some very large numbers, and while there aren't a lot of them, because the histogram is not very tall in this range, while there's not a lot of them, just the fact that they're so large on their face value pulls the average up, pulls up the mean. And that makes the mean greater than the median when you're dealing with this skewed right situation. Mm-hmm. Yeah, if you were to do a histogram here, what you'd do is you'd make your frequency diagram. You'd have everything from 0 to 50, then 50 to 100, and really that should be 0 to 50, 51 to 100, 101 to 150. And then you'd count up the frequencies of each of those and plot those on a histogram. Yeah. Again, we're not super, it's not like the most important thing we want to stress. I like to look at just kind of the numbers as they are. Finally, the last major, so we have the 3 M's, the mean, median, mode. There's also something called the mid-range, which is not super interesting. We'll talk about it for like a hot second. It's literally just the average of the smallest and largest value in your data set. Okay, cool. It's not that interesting, but we'll talk about it. The mode. Now, the mode is actually surprisingly, it seems to be the simplest one, but I can give you some confusing ones here. I can make it confusing if I'm bored and just trying to, make your life more difficult. And when will I make your life more difficult? Is there some kind of rigorous standard I used? No, it depends on how I'm feeling that day, right? No, I'm kidding, no. Anywho, the mode is the data value or values that occur most often in a data set. So here's the thing. Notice it has to occur the most often. That means it has to occur more than some other number. So something can only be a mode if there's something that's weaker than it, that's lesser and less prevalent than it. But if you have a bunch of numbers that tie for being first place, for being the most frequently occurring value, and then you have some that fall beneath them, you can actually have more than one mode. It's whichever one's tied on. If everything occurs exactly the same amount of times, say everything occurred once, or somehow you have some weird freaky data set where every value occurred exactly twice, no one value dominates and is more prevalent than the others, you can actually have no mode. The mode isn't 0, the mode is just not there, there isn't one. No mode arigato. So the mode can get really funky really fast. So if you recall, we looked at this information. The physical therapist was talking about what her clients, their most frequent issues that they've been having, their complaints and whatnot. And let's see, we had back, we can have wrist, elbow, hip, shoulder, knee, and hand. You can have those kinds of injuries. We'll make a quick frequency distribution for this so that we can see, hey, which ones are occurring the most, which ones are occurring less than that. So back, let's count. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ooh, I bet it's the back, and I bet that is what the person who is saying here. Neck, let's see. The back had what, 12 occurrences? Wrist, I see 1, 2. Did you see any more wrists than that? I think it's just gonna be 2 wrists. Elbow, 1. 1 elbow. Hip, you got 1 person with hip issues. 2 people with hip issues. Shoulder. 1. Oh, I see what you're saying. I forgot neck. Yes. So this chart's not large enough for that. That's okay. We'll just throw neck there at the end. Pretend the chart was a little larger. Yeah, shoulder. 1, 2, 3. No, there's 4. Yeah, it's kind of hard to see that. So there's 4 shoulder injuries. Knee. 1, 2, 3, 4. 4 knees. Hand injuries, you got 1. And 2, that might not be perfect here. 2 hand injuries, and finally neck. We got 1, 2 neck injuries. The mode is the data value that occurs the most, and it's clearly going to be the back. Because it occurs the most, it occurs strictly more frequently than other data values in the set. So back is the mode. It's the single mode. It's the only one. Let's play with the data a little bit. So in that one, it was interesting. Let's play around with it. Let's say the elbow also had 12. And so, you know, this is no longer perfectly reflective of the data above. Let's say there were 12 people who had elbow issues and 12 people who had back issues. What would you say the mode is in that case? Exactly. It is both the back and the elbow. So there's actually two modes. And one of them is not more dominant or more important than the other one because they both appeared the same number of times. There's two modes in that case. What if we also threw in, hey, the shoulder has 12 as well? What would the mode be in that case? Or modes? Yeah, all three of them, exactly. There's now three modes. Back, elbow, shoulder. There's three different modes there because there's three. They occur more frequently than the others, but they're tied for the lead, and then there's some others that fall behind them. So there's three modes in that particular case. What if, and we're just having fun with this here, what if the shoulder actually had 14? What would the mode or modes be in this case? Just the shoulder, yeah, exactly. The only mode would be the shoulder. Because while the back and elbow are close and they have a lot of occurrences, they're not quite the leader. So they're gone now. What if we did something real silly? How many of you want to see me get real silly? Anybody? Not too silly, Mr. Gunther. I know, it's wow, guys. What if all of them occurred exactly 4 times? The back, elbow, wrist, hip, shoulder, neck, hand. What if every single one of them occurred exactly 4 times? You're tempted to say it would be all of it, right? Remember there's no mode. The definition of mode is that it's strictly more. There can be multiple modes, but there has to be something that falls behind them. They have to be a leader in some way. In this case, they're all exactly the same. There's no leader, so there's no mode. So you can have a leader or leaders, or you can have no leaders at all, if they're all exactly the same. You are thinking like a statistician. Yeah, what if we played with it some more and said, okay, everything was 4 except the neck only had 1 injury. Now we do have leaders. The mode would be all these things. They're all tied for the lead, but there's something that straddles behind. So now the mode is back, wrist, elbow, hip, shoulder, knee, hand. They're all got an equal claim to the mode. One of them is not more prevalent than the others. Great question. So yeah, as you can see, things can get really wild here really quickly. Let's play a little bit with this. Find the mode. What would you say? The data set is the numbers 8, 2, 4, 6, 8, 10, and then 8 again. What's the mode?
8.
Yeah. Looks like 8 occurs 3 times. And then the other data each occurs just once. So 8 is the clear leader. It's important to note then, you can have a mode then of a qualitative data set. Because that last example, the data set, the data was not how many of each there were. The data was the actual injury themselves. The data was back, neck. The first person's data was back. The second person's data was neck. The third person's data was neck. Fourth person's was hand, and so on. So unlike the mean or median, the data itself can be qualitative or quantitative when you're talking about the mode. But for the mean and median, the data has to be strictly quantitative because you're not going to take the average of neck, back, shoulder, hip. That doesn't make any sense. They're not numbers. How do you add back plus hip plus, it's nonsense. So the mode can actually be, it's one of those few nice measures that can apply to qualitative and quantitative data. Okay, let's see this next data set. 3, 7, 3, 8, 3, 9, 6, 9, 8, 9. What would you guys say is the mode? 3 and 9, exactly. 3 occurs 3 total times. 9 also occurs 3 total times. Now 8 occurs twice. So just because something occurs multiple times doesn't mean it's automatically a mode. But yeah, the modes would be 3 and 9. Down here, 5, 7, 9, 10, 3, 6, 8, 4. A little song there. Do you guys see one that's more prevalent than the others? No. So this would be no mode arigato, Mr. Roboto, as the ancient verses doth sing. So there's no mode of that data set. No, in reality, the numbers here are nice and clean. We got 8s, 2s, 4s. They're all nice positive integers. Real data, though, it can be like 8.4, 2.7. And the mode would still be there. 3.8 and 3.9 are not the same number. So you can't just say the mode is based on being in a ballpark. It has to be a specific number. So we've got, and there's a blank page here. We got a nice little chart here. The mean, you can have the population mean, mu, or the sample mean, x bar, and it just depends on the context that you're using it in. You need to know the context. And by and large, you're going to be using the sample mean to draw inference about the population mean it came from. This is like a physical interpretation of the data. If you were to like try to import it into physics, the center of gravity is the population mean. It's basically the point where something rotates if you were to throw it in the air, something like that. But we don't care about that. We don't care about physics. If you're curious, then the next section, which we'll do next time, the standard deviation is related to something called the moment of inertia. The moment of inertia, which describes something's tendency to rotate, if you like physics. So we talked about mean, median, mode. It's pretty straightforward. We'll add one little thing in there. The mid-range. I don't think it gets like a nice special symbol. I think we just say, this is the mid-range. All right, freedom. So we have one other thing called the mid-range, and it's rock simple. It's just the average of the smallest and largest values only data set. So you take the minimum,
How
the
to
smallest
take a
values, plus the
screenshot
maximum,
on
the
my
largest value,
HP laptop.
and divide by 2. Bada bing, bada boom. It's not that difficult.
From HP Store.
For the mid-range. You might see like one homework problem over it. It's not the most interesting. In fact, we can go do a quick example of mid-range. Let's go all the way back to, let's go even further back. Let's use the data for the 7 employees at the company. We'll say we're doing the mid-range. It's very straightforward. You take the smallest, not the first and last number, because that's arbitrary. You take the smallest number, which in this case is 5, plus the largest value of the data set, which is 43. You take the average of just the 2. So you don't divide by 7, you divide by 2, because you're only taking the average of 2 values. So 5 plus 43 is 48, divided by 2, you're going to get 24 as the mid-range. The show with Kiefer Sutherland. So that covers the first section of chapter 3. That's going to do it for today. I'll be posting your exam grades a little bit later today onto Canvas, the official grade book of the course, and the official grade book of the Dallas Cowboys. You guys have a wonderful day. Thank you so much.